Okay, sorry for the delay. So I had some problems connecting to Zoom again. I'm using my phone, but my battery is low. So, but I hope once we're in Zoom, I can just change to another network and it should be okay. So today we're going to move on to a new topic, which is called Apache Pig. What is Apache Pig? Well, let's have a look. So if we think about what we're doing in the last lab, there's a lot of Java coding, right? But we could probably write a query to capture the same thing we're trying to extract using SQL, yeah? So if we look at the version in Hadoop, we have all of this Java code and lots of declaring what types are and all of this Java boilerplate. So this is kind of maybe a bit frustrating. So people thought about what would be an easier way to program these sorts of tasks such that they run on Hadoop. So one idea would be to just use SQL, right? So here we have an SQL query that corresponds pretty much to what you were trying to solve in the last lab, yeah? So we have some joins, and then we do a group by, and then we order by descending. And this is pretty much expressing exactly the task that you saw in the last lab, right? So this would be a lot more convenient to do. So why don't we use SQL? Why don't we just do this? It's a lot easier. I can stop wasting your time and we can just write SQL and we're done, right? Any ideas? There are things that are, yeah. So we might sometimes want to process data that are not structured like a relational table. Yeah. In the case that the data are, that's a really good point. In the case that the data are structured like a relational table, why not use SQL then? So by putting the different instructions, by having more imperatives, that we can do things in parallel. Yeah, so that's a really good point, in the sense that if we look at SQL, one of the major obstacles we have is that the engines, relational database engines, are not typically built for large workloads. Yeah, they could manage probably what we did in the last lab. Yeah, if you left Postgres, if you indexed all the data in Postgres and ran this query, I did it once. I think the query took about 30 minutes and it eventually did it, right? But we're only working at this scale because there's many of you. So the idea is, what would happen if we had 100 times more data, right? So relational database engines tend to focus on OLTP processing, online transaction processing, where they process lots of transactions to find out the data for a particular client or a particular product, or to update some data. They're not really very good for OLAP, online analytical processing, sort of analyzing the entire data set to extract some analysis. The other main issue that we have with relational databases is that they're thought of as a way to index data on one machine. They don't easily distribute, yeah? So these are some answers why we're not just using SQL, but in fact, these are not very good answers, because the question is, why not use SQL? Whereas the answer is, why not use typical relational database engines? So what's the difference? When we talk about SQL, it's a language, right? So why couldn't we not just take this query here and interpret it into some sort of MapReduce distributed processing? Yeah. So this is a kind of an interesting idea. What if the user could just write this, and in the background, this would get compiled into all the Hadoop jobs that we want to do? So this is one of the ideas behind Apache Pig. It's basically a higher level language. That's not SQL. There is another language I'll mention briefly at the end called Hive, which is much more SQL-y. But it takes a lot of inspiration from SQL, and it's much higher level than Hadoop. Yeah? So Apache Pig. So we can create MapReduce programs to run on Hadoop. We are going to use a high-level scripting language called Pig Latin that will be effectively compiled into Java Hadoop jobs. And we can also embed some Java functions as well, which we couldn't do in SQL. This for the less structured data. Yeah. So Apache Pig, the framework, is based on this notion called pig relations. Okay. So ahue, langue, le, iste, este. So I don't know if anyone has heard of Pig Latin. I don't know if there's a version of this in Spanish, but essentially it's this sort of children's game or children's language where you take the last consonant or the start of the word, the first consonant, you stick it on the end and then you stick a on it, AY. So this is, what language is this, right? So language, you put the L at the end and then you say A. So it's this secretive way of talking called Pig Latin. So chicken soup would be ikin che upse. It sounds vaguely Latin, apparently. I don't think so. Whatever. I'm not an expert in Latin. Is there anything similar in Spanish? Yeah, I think so. There's maybe some similar games or languages in Latin. So this is why it's called Pig Latin. Yeah. Okay. So in this case, maybe approximating SQL. So we'll have a quick example of what something would look like in Pig. So we have a very massive, you're working in a supermarket, your boss has given you this very massive text file or TSV file, which is transactions, where we have customers, products, times, and prices. Yeah. And what your boss would like to know is the number of items sold per hour of the day. We're not interested in prices in items with price less than 1,000, which is to say we're only interested in items with price greater than 1,000. And we want to count each item per transaction only once. So if a customer buys 2 Nescafes in the same transaction, then we just want to count that once. Yeah. So let's have a look how this would look in Pig. We'll look at an example first, this example, and then we'll go and look at the language in more detail. So first thing we can do is we can register a jar file. You all know what jar files are at this stage, which has some functions that we can call Java functions, yeah? In case there's some unstructured or not ideally structured data that we'd like to manipulate, yeah? So we can do user-defined functions in Java or Python or Ruby, or there's other languages we can use. And this is an example where we're going to extract the hour from that strange date we saw earlier, yeah? So we have some Java code that will take an input tuple, an input line, and will extract for us the hour. Okay, so we're going to load these data into Pig storage, and we're going to indicate that they are separated by tab, because we're civilized people, and civilized people don't separate by comma, they separate by tab. It's TSV. So we have afterwards a definition of a header. We're going to say that there are 4 columns, one for customer, one for item, one for price, one for time, and one for price. Okay. So we're going to view data as a relation, as a streaming relation. The idea is we're going to be, like in MapReduce, processing each relation or each table tuple by tuple. Yeah. So this streaming relation has fields, customer, item, etc., time, and price, and it has tuples. It has data. So here's an example of where our view, the Pig view of this data would now be. Yeah, we have a relation, we have a table, which is called raw, and we have the 4 columns, right? So we parsed from the raw TSV file directly into this Pig relation. Next, we're going to filter the raw details. We're not interested in these cheap products that are less than 1,000 pesos. So we're going to filter and keep the ones that are greater than or equal to 1,000 pesos. So we're going to get rid of the first line. Yeah, so we call this filter operator on the raw relation, and this gives us a new relation. Yeah, so like in relational algebra, we're transforming relations into other relations. Yeah, transforming tables into other tables until we get the answer we're looking for. So now we have this premium relation. Yeah, we've gotten rid of all the cheap products. What would we like to do next? We would like to apply a group. We would like to extract from the time. We'd like to extract the hour of the day. So we're interested in that it's 8 a.m. Yep. So we call here our user-defined function with the package name and then the name of the method, extract hour, time, and this will return for us the hour. Yeah, so we call some Java code to extract the hour from that full thing. It could also be Python, or it could be Scala or other code. Okay. Next, we're not interested in counting the same customer buying the same item at the same price at the same hour. So we're going to apply a distinct, and this gets rid of all the duplicates that are in our relation. Yeah. So we store this as a new relation called unique. Next, we're going to group by item and hour, right? So we want to count pairs of item and hour. So we want to know how many times, for example, was Nescafe bought at between 8 a.m. and 9 a.m. Yeah. So here we will group by item and hour, which will give us this strange relation here, okay, which we wouldn't really have to manage in SQL. SQL generates this sort of thing, but we always have to flatten it immediately using an aggregate function like sum or count or whatever. But in Pig, we can handle these sorts of relations. I'll describe how that's done later. So we have this strange relation where we have a key, which specifies a group like Nescafe 08. And we have all of the tuples where the items Nescafe and the hour is 08 here within this group of tuples. So what we're going to do next is we are going to reduce this to a count. We're just interested in counting how many tuples there are in each group. Yeah. So we apply this for each generate, which is essentially a projection. It's like the select of SQL, where we say we're going to flatten 01, and we are going to count the number of tuples here as our count. And this generates for each group the count of the number of tuples here. So essentially what it will generate for us is this result here, where we have the groups and we have the count. Yep. And we can order. Yep. So we can then order this by descending, because we want to know which products are sold most in which hours of the day. Yeah. So we sorted, and we sorted by descending because we're interested in the most frequently sold items. Yeah. So, okay, here the count is 3 and 1, because just based on the small snippet we saw, but probably this would be a different result. Yeah. So we order by descending. And then finally, we can save our Pig relation to a file, right? So we just say, store this into output.txt or output.tsv. Yeah. And we're done. So we have our pairs of products and hours of the day, along with the counts of how many times they appeared. So this is an example of a Pig script. This would then be compiled into Hadoop code. Yeah. So there will be a Pig interpreter that will take this script and say, okay, we need these jobs here, and compile the Java code, and it will run as Java code in Hadoop. Any questions or doubts? Does it look nicer than coding in Java? See some heads nodding. Yes. So yeah, so essentially this came about because people were using Hadoop. They found it difficult to program. They wanted, there are people who are analysts or data scientists who maybe didn't have so much experience with programming, and they wanted a higher level programming language. So for running Hadoop jobs. So the cost here is efficiency. This might not be as efficient as if you some expert program this directly in Java. Yeah, as is the problem with all high-level languages. Okay, so we're going to talk a little bit more in detail about the language. So the first thing is the schema. So we have these Pig relations, which are like relational tables. So tuples can be incomplete, like in relational tables, we can have nulls, and relations are by default unordered. Yeah, so much like in SQL. So we have a Pig schema, which has names for fields. Yeah, so customer, item, time, price, very like relational database. So we have two ways to reference fields. Or attributes or columns. We can reference by name. So for example, here we say price, or we can reference by position. Yeah, so here we say $3. So if we count here, we see this is the fourth column, so we can deduce that $3 starts at 0. Yeah, so $0, $1, $2, $3 gets us to the fourth column. Much more readable to use the name. Yeah, so if it has a name, better to use it. Okay, it's more flexible as well if you change the schema later. So what do we have? As well as names for the columns or the fields, we have types. Yeah. So we have char array, which is essentially varchar in SQL or string in most programming languages. We have date times, we have int, and so forth. So here's a list of the most common types we have. Yeah. Int, long float, double, big integer, big decimal, Boolean, char array, byte array, and date time. So byte array is just an array of bytes. What happens if you omit types? You can very happily do that. The fields will default to the most generic type, which is a byte array. It's a bunch of zeros and ones. Yeah. There are implicit conversions possible in Pig. It will try to deduce correctly what type of thing it is based on the operations. Yeah. So what is sometimes called duck typing. Do you know why it's called duck typing? There's a saying in English that if it looks like a duck and it quacks like a duck, it's probably a duck. I don't know if there's a similar, I don't know of a similar equivalent in Spanish, but so if it looks like an integer and it quacks like an integer, then it's probably an integer. Yeah. So in this case, if we load our data without specifying the types and then we do some sort of numeric arithmetic, we can probably guess here that hour is an integer. Yeah. So we can do the duck typing and the conversion will be implicit. Sometimes it will generate a warning for these implicit conversions. So it's not a bad idea if you know the type to specify it. In this case, if we say for f, which is a float, then in that case, we could guess that the hour is a float. Okay. So there are some more complex types beyond the integer and the string and the dates and so forth. There are also tuples. Yeah. So we can represent inner relations. A single field, a single column can, in some sense, represent multiple values. Yeah. So here we have some data. This is in the Pig syntax. This would be in the Pig shell. So we see that we have a tuple of 2 elements, and the first element is a tuple of 3. And the second element is a tuple of 3. Yeah. So if we load this data, we can load it as 2 tuples, T1 and T2, where inside each tuple we have 3 integers, T1a, T1b, T1c, and T2, T2a, T2b, T2c. Yeah. So we can represent nested tuples. Yeah. So what would this look like from our Pig relation? It would look something like this, where we have this T1 and underneath the T1a, T1b, T1c, and T2, T2a, T2b, T2c. We dump, this is essentially we get back the same data as we had as input. So how do we work with this? If we wanted to reference T1a, for example, to project T1a, we can do T1.T1a and then T2 $sign or pesos 0. Yeah. So this would allow us to access, using the dot, we can access the inner parts of the tuples. So this would just generate from these 2 columns, generate a new table, which would look like this. Yeah, this would be called T1a and this would be called T2a. And we can dump that and get our 3 tuples back. Okay, what about bags? So what are bags? Does anyone know what a bag is? A multi-set? Have you heard of multi-sets before? So there are mathematical structures. So we have sets in maths, which are unordered and do not allow duplicates. Yeah. We have lists or sequences that have order and allow duplicates. Yeah. We have bags, and in the case of bags, we allow duplicates and we have no order. Unordered, but we can have duplicates. Something can appear more than once in the bag. So this is called a bag or a multi-set in mathematics. So in terms of the bag, how does it work? My phone is ringing. It's a very strange number. 603,000. Sounds like it must be the government or someone, I'm not sure, who has such a round number, but anyways. So we're going to, why do we need bags, right? So we can load data into a relation A, for example, like this. And then we can group the data. So this is a normal relation, but when we group the data by something, this is the most common source of bags. Yeah. So what we have now is a new weird relation, which has 3 rows. Yeah. But in each row, we have a bag of tuples associated with each group. A bag because the order doesn't matter, and we can also have duplicates. So in the first group, we have a bag with 1 tuple. In the second group, we have a bag with 2 tuples. And in the third group, we have a bag with 1 tuple. Yeah. So how does this look in terms of pig syntax if we actually ask pig to dump it in its own syntax? Here we have the representation where we use these braces in order to represent the bag. Yeah. So it means that what we have really here are 3 rows. Yeah. So we have a row for 1, a row for 2, a row for 3, and then we have the groups. Yeah. So we have the bags associated with each group. All of the tuples that have 2 as its first value, all the tuples that have 1 as its first value, all of the tuples that have 3 as its first value. So this is a bag, and we can access this structure. In SQL, you cannot access these sorts of structures because if you apply a group by, immediately you need to count, or you need to sum, or you need to flatten somehow. You need to calculate something over this group and return that result. But in Pig, we can actually work with this intermediate group data if we like. So these are bags. Any questions or doubts so far? Okay, well, good. So we have tuples and bags. So how do we work with tuples and bags? There are some operations that we might like to apply. So the first is the notion of flattening tuples to get back to a simpler relation. Yeah. So here we have a pig relation that has 2 columns, and in each column we have a tuple of length 3. Yeah. So we have our T1, T2 example again. So this is how the relation looks. Yeah. Sometimes we might want to unnest the structure or somehow get back to a simpler structure. So how do we do this? We can do this by using flatten. So if we look at the syntax of A at the moment, we see that, yeah, it's the same as what we loaded. We can then apply these flatten functions, T1 and T2, which essentially says unnest T1 and unnest T2, simplify the structure of the relation. Yeah. So what we get as a result in X is this structure here, where we now have 6 columns rather than 2. Yeah. So we somehow unnest and simplify the relation, and we go back to a much simpler relation. If we dump X, we see now that we have 6 columns, each of which has an integer, rather than 2 columns with tuples of 3. Yeah. So in this case, what happens if we flatten only T2 and we leave T1 as it is? Yeah. So here we're essentially projecting T1 and flattened version of T2. How many columns will we have in the output? Any ideas? So we're going to keep T1 as it is, and then T2 we're going to flatten. 4. Yeah. We're going to have 4 columns like this. So T1, T2A, T2B, T2C. And within T1, we have 3 columns because they're tuples of 3. Yeah. So this is also perfectly fine. So we dump this and we see that the structure now, each tuple it's a 4 tuple, and the first element of the 4 tuple is a 3 tuple. So for bags, we can also apply something similar. We can also apply a flatten operation that's very similar to a Cartesian product. Yeah. So given this sort of weird nested structure here, what we have are 3 rows. So 1 for 1, 1 for 2, 1 for 3. And within the 2, we have a bag of 2 tuples. In the group of 3, we have a bag of 1 tuple. And in the group of 1, we have a bag with 1 tuple. So for each B, what we'd like to do is flatten A. Yeah. So what does that mean? Essentially, we return from the bags, we go back to a simpler relation again. So basically what we're going to do is get back to the original A. Yeah, we're going to create a C that's basically like the original A. Okay. So we're going to extract all of the tuples from all of the bags in that column and create a new relation. Okay. So what happens if we try to project this column and then flatten A? In that case, within every group, we're going to apply a Cartesian product. Yeah. So what this means is that essentially we're going to end up with this relation here. Somebody's calling me again. So what does this do here? For every group, we apply the Cartesian product with its bag. Yeah. So we take every combination possible. So we take this group here and we do the Cartesian product with all the tuples in this bag. We take this value here and do the Cartesian product and so forth. So we concatenate all of these things together and we produce a new table that looks a lot simpler like this relation D here. And we dump it and we see we have a relation with 4 columns. Any questions or doubts with that? No? Okay. So all good. So in terms of the other features of the language, we talked about the types. We have some basic operators, comparison, not equals, less than, greater than, equals, arithmetic. We have this reference operator, which we already saw, T1.T1a. We have some Boolean connectives and or not that we can apply, for example, to create more complex selection criteria. We have some casting operators, as we saw. We also have some conditionals, so we can do the ternary operator. Have you seen this before in some other programming language? Yep. Yeah. So we have a condition and then a question mark. If the condition is true, then we'll return this value, and this is like the else. If it's not true, we return this. So if the hour is greater than 12, we'll return PM. If not, we'll return AM. So this is called the ternary operator. It's an abbreviation in many programming languages. Or we can be more explicit and do a case conditional. So case when hour greater than 12, then PM. We can do various cases and then end with else. Okay? Else AM. In this case, we only need one case and an else. So we also have operators for grouping. So we can apply group by. So we can do, for example, group the premium relation, as we saw earlier, by item and hour to gather all of the tuples with the same item and the same hour together into a bag. Or we can apply co-group. I don't think co-group exists in SQL, but SQL is thousands of pages long, so maybe I'm wrong. But co-group, essentially the idea is that we can actually group multiple relations. So it's equivalent to like taking the union of both relations and then doing a group. Yeah. So in practice, we can actually use co-group for a single item, or we can use group for multiple items, but co-group is considered more readable for multiple items. So co-group is like taking the union of premium and cheap and then applying the group by. So we can do all of that in one command. So we have some aggregate operations, which are the same as SQL. So we have average, min, max, sum, count. We have size, which is a little bit different, and concat. So size is the same as a count on bags, but it can also be used to get the number of elements in a tuple or the length of a string. So it has some other features or output for other types of data. Yeah. So we have our typical aggregate operations like you would have seen before in SQL. We also have joins. So if we take an example of some joins, we have some data here where we have information about Nescafe, the hour, 8 a.m. and the price, 120. Seems cheap. Maybe it's not maybe it's the number of times the product's been, yeah. So I guess this would be the number of times this product was bought at this time. So this says Nescafe, 8 a.m. has been bought 120 times. Yeah. El Mercurio has been bought 142 times at 8 a.m. and so forth. And here we have data about the price in another relation. Yeah, so we have 3 example tuples. We have price 2000 Nescafe, price 8,250 and so forth. So we can load these data into big relations. And then if we want to join them to get the prices, to join all the data together here, we can do join A by product, B by name. Yeah. So here we see that the product is called product here. And here when we loaded the data, we call this column here name. So we just say join A by product, B by name, and we'll get X, and X will provide us with these data here. The result of the join between A and B. We dump the data and we see that we have tuples of 5. And yeah. So this is your typical inner join. So we have in Pig, we can apply inner joins as we just saw. These are the defaults. So if you don't specify anything, just say join. It's going to be an inner join. We can also apply a self join, which is this idea of joining a relation with itself. Yeah. So we just join one relation by itself. If you do this in Pig, and this may or may not be an issue for the lab, we'll see on Wednesday. You cannot do it directly because we have streaming relations in Pig. So it means that we're going to read through the relations once and we can't read it again a second time for the self join. So how this works for Pig is you need to create a copy of the relation, and then you need to join the original relation with its copy. So so the self join, you need to copy the alias. You can't do join A by product A by product. Yeah, you'd have to do join A by product A copy or A prime by product, something like that. We also have outer joins, so we can apply a left, right, or full outer join. You remember what outer joins are, I hope? No? Let me see. So, yeah. So let's say we change this to a left outer join instead of saying join. Yeah. So what will happen is that we will keep the data on the left, irrespective of whether there is a match on the right. Yeah. So it basically means that if we don't find the data on the right, we keep the tuple from the left and we add nulls to complete the data that should have come from the right. Yeah. So in this case, the result of a left outer join would be exactly the same because all of the tuples on the left have matching data on the right. Yeah. If we did a right outer join, so if we made this a right join or right outer join, it would not be quite the same. What the right outer join will do is keep all the data on the right, no matter whether or not they have a match on the left. Yeah. So it means that from data 2, we would maintain all of these data here. Yeah. Irrespective of whether there is a matching product in data 1. So if we apply a right join, we would additionally have a result, which would be null, 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 8,250, Gillette Mach 3. Even though there isn't a match, we would keep that on the right. Yeah? That makes sense? Okay. And then the full outer join is just like the union of left join and right join. So we keep the data from both, even if there isn't a match on either side. We can also do Cartesian products, which are probably not recommended at large scale, but a Cartesian product, if you have a table or a relation with 20 values and with 20 tuples and a relation with 30 tuples, and then we'll create a relation with 600 tuples. You could maybe use this if you had maybe a relation that just had a single value that you wanted to append as a column, but in general, it would not be wise to do a Cartesian product over two very large relations. Yeah. It will just explode. Okay. So how are the joins implemented? They will be translated into MapReduce jobs. So you already saw in the lab, last lab, how we can do some joins using MapReduce. Yeah. So in this case, in the case of the last lab, it was a self join. Yeah, we're joining movies on movie to get pairs of actors. Yeah. So in this case, Pig will be running something similar to implement joins in MapReduce. We can specify some parameters in terms of how they will be implemented. So we can, for example, specify how the data should be partitioned, how the data will be sent to different machines. We can also specify the parallelism. So we can specify the number of reducers, the machines that will take the data and apply the join after the map. How many machines we want to use for that. If we want, optionally, we can specify these details if we want to use a different type of partitioner to the default. Yeah, so when we do joins, as you saw previously, I conveniently named in data 1, I call this product, and in data 2, I call this name. I give them two different field names. what happens if we have two columns with the same name and we do a join? Well, the issue then is that we'll have a relation with 5 columns where 2 of the columns will have the same name. Yeah, they'll have this product name here. Yeah. So what happens in this case? Well, the relational algebra strictly forbids this sort of case. We can't do a join or a Cartesian product between 2 relations if they share an attribute. In this case, Pig is more relaxed and says, hey, that's okay, you can do that, that's no problem. It will run X, it will run this join, and it will create a table, a relation, where 2 columns have the same name. Yeah. So if we, however, tried to project later from X and say, give me the product name, we see that we have a problem. Yeah. Because we're trying to reference an ambiguous column. So which product name? At this point, Pig will complain and say, hey, you need to be more specific. This isn't sufficient. So Pig allows this mechanism for disambiguation, which is maybe similar to ideas in SQL, where we can create aliases for relations. But here the syntax is a little bit different. So if we wanted to refer to the product name that came from the relation A originally, we can use A : product name. Yeah. Now you might say in this case, I mean, what's the problem? A product name and P product name will be equal. Yeah. But that's not necessarily always the case. Yeah. We could also have some other columns that are the same that are not used in the join that will have different values in the same row of the join. So it may not always be the case that we're so interested in this. Any questions or doubts? No? Okay, so we have a few more operators to go through, and then we're pretty much done. And if there's questions about the lab, we can stay around. I can answer them after. So this part we can go through relatively quickly, but if there are doubts, just let me know, because I think from SQL it's not difficult to understand what's going on. So okay, we have this operator called filter. What filter does is essentially a where in SQL. Yeah. So we'll take the raw data and we're going to say premium equals filter raw by price greater than or equal to 1000, and it removes, it keeps all of the values that, or all of the rows that satisfy this condition here. Yeah. So we keep those that satisfy the condition. Split is an interesting one. So if we wanted to somehow separate our data into 2 or 3 or 4 or however many, and analyze the different splits in different processes, we can use this split function. So split basically takes an input relation, raw in this case, and it says we're going to split into cheap if price is less than 1000, which will gather all of the products that are priced less than 1000 here, and premium if price is greater than or equal to 1000, which creates this second relation here of all the more expensive items. And we can do this for multiple things. Yeah. And then we can create different data processing pipelines for both. Maybe we want to analyze the different types of products in different ways.
We don't have to define cheap and premium in this case.
No. Another interesting thing here is that we don't have a relation equals at the start, because it doesn't return a relation. The relations that are returned or created here are named directly in the split. Yeah, so we don't need to define them cheap or premium before. They're created here.
Oh, and then I can access to
cheap and premium as if it were any other relation. Yeah. Okay. So we take the same step again. We have cheap and premium. What if we want to go back to all? Well, we can apply union. Yeah, so we just do all equals union cheap, comma, premium. Order. So if we want to order, as we saw before, we can order by ascending, we can order by descending, we can order lexicographically according to a number of columns. So what this says is order raw by price ascending, and in case of a tie on price, use customer descending to break the tie. And then the order can be arbitrary if there's still another tie. Yeah. So we can do order by, which is very similar to SQL. Here we have the results. We can apply order and limit. Yes, so we can apply our ordering and then say, I'm interested in the top 2 after we've applied our ordering. So we can call top equals limit order 2 to get the top 2. We can apply a sample. So we can say, hey, I would like to have some percentage of the tuples. I'd like in this case, 50% sample, yeah, which would be kind of rare in practice. But so 0.5, I say sample raw 0.5. This is probabilistic. It will generate some sort of random number for each line. If it's above 0.5, it will output the line. If not, it won't. If we wanted a 10% sample, 0.1, and so forth. So here we have our sample. We can apply rank. I think this is slightly out of order. I was changing these slides just before the class, but anyways. So we can also apply a rank, where in this case, if we apply the order, we can also specify rank, not just order by, rank by. And this will generate an additional column called rank that will give the position of the element in the row. We see that it's the same as rank in SQL in the sense that if there are ties, we'll give the same rank. So we'll go 1, 2, 3, 3, and so forth. Yeah. So we have 3, 3 here because it's tied on price and tied on customer, which were the elements of the ordering I mentioned here. Yeah. We can also just rank raw, and that will just generate IDs from 1 to n. That slide is missing. So if we omitted the buy and the price and the ordering, we would just generate an enumeration from 1 to n of the rows. Any questions or doubts? So that's pretty much the core of Pig. Yeah.
I don't get it. Sorry, but the difference between split and boolean.
Yeah. So one is kind of the opposite of the other. So from split, given one relation, we can create multiple. We can create, in this case, 2. Yeah. In the case of union, given multiple, we create one relation. So we can merge multiple relations back into one relation. So they're going, it's almost like union is undoing the split here, which it doesn't have to do. We can take whatever relations and do a union. Yeah. But yeah. So they're almost like inverse operators. Is that clear? Yeah. All right. Sample rank. Okay. Any more questions? Okay, so we have to be a little bit careful often with nulls, as in SQL. So we have to be careful when we have nulls. It's very common if we're working like MapReduce, Hadoop, and some of the frameworks we'll see later, that we might be working with noisy data that are not strongly normalized. Yeah, they might have nulls, they might have incomplete rows. If you've worked with data from Kaggle before, these sorts of sites where you download some data set and start to play with it, you notice a lot of noise, there's missing values. So we have to be a little bit careful, or it's always, important to be mindful of nulls and what they mean. So nulls represent incomplete information in most cases. Maybe sometimes values are deliberately oppressed. Maybe sometimes values just do not exist. It's not just incompleteness, but maybe some product has no price or has never been bought, or at any hour of the day, whatever it might be. So here we have some data. Here we see the representation for nulls. Essentially, they're just the empty string in Pig, in the normal Pig syntax. So we have a null here because we don't know how many times Nescafe was bought at 8 a.m. And we have a null here because we have a product that was bought 153 times at 9 a.m., but we don't know the name. Here we have some other example data where we have, this is the same data. Yeah. So we have 2 nulls in the data. Here we have some more data where we have a price for some product that we don't know, which is a null. We have the Gillette Mach 3 cost 8,250 pesos. And we have El Mercurio, which has no price. Okay, so if we load the data, into A and B, and then we do a join into the result of X. Yeah. And the question is, what should X return for us? So how many tuples do we think will be in X? We're doing an inner join here, a standard join. So we're joining product name by product name. So we're joining this column here with the second column here. Yeah. So for Nescafe, the question is, how many results would we return? And the question is, does Nescafe join with a null? So what would happen in SQL in relational databases? What joins with nulls? What about this null here? Would this null here join with this null here? Is null equal to null? Are constants equal to nulls? So nulls are not equal to anything. Yeah. So what we'll get if we dump X is nothing. Yeah. Ah, sorry. Yeah, we get El Mercurio. There's a match on El Mercurio, so we have a null here. However, on the join, nulls won't match nulls, nulls won't match other constants, nulls won't join with anything. This is the same as in SQL. Yeah, so if you do any sort of comparison with null, it returns unknown in SQL. And it's a similar situation here. Okay. Any questions or doubts? Okay. So how do we run Pig? Okay, this is Pig. This is all wonderful. That's the language. There are all these operators, high-level language, nice and concise. How do we use it? So Pig will be translated to MapReduce and Hadoop, yeah, as mentioned before. So there's no Pig infrastructure or Pig framework or anything like this. There's an interpreter that takes the Pig script and compiles it into Java code that's compiled into a jar and launched on the Hadoop framework. Yeah, it's just a surface level scripting language for MapReduce, for Hadoop in particular. Yeah. So there are 3 ways to execute Pig. When you're developing your analysis for the first time, the best way to do this is probably in this REPL way, in the scripting language. Have you heard of REPL before? It's a read, evaluate, print loop, I think. Read, evaluate, print loop. It's this idea of entering things line by line. You enter a line of code, you see some results. You enter another line of code, you see some results. You enter another line of code, you see some results. Yeah. So line by line. Yeah. So every line has some sort of effect. Yeah? So Pig is essentially a REPL language, and the grunt script, this is the shell of Pig, allows you to see what's happening line by line. Yeah. So you can run it with grunt. If you run things in grunt, commands are run lazily. So often it won't run everything until it really needs to. Yeah. So for example, you could do filter by price greater than 1,000, filter by hour less than 8 a.m. Yeah. If you were to run each of those jobs separately, it would launch MapReduce jobs. But clearly, you could very easily combine both of those filters into one job. Yeah. So it's more efficient for this to be evaluated lazily. Yeah. Not to execute every line every time on Hadoop, but to wait to see if maybe you can combine several lines into one job. So with the grunt script, you can just call line by line the different functions, the different lines of code that you'd like to run. This is very useful for developing a script for testing your code on a small example. You can also run Pig in local mode, so it doesn't touch MapReduce. It kind of emulates it locally, so you don't have all this network overhead for processing. Like what would be really common would be to define maybe an example of 10, 20 lines, develop your script in this way, test it locally over a very small file, and then when it seems to be working, try launch it on the full thing. Yeah. So when you want to launch it, you can just call your script. You can save your script in a text file and then just call pig word count.pig or whatever you want to do, which will launch your script. So this will be then run. This will be the most typical way once you've developed a script to launch it. You can also from Java code in Hadoop or from Pig code, you can call Java. You can call them from either direction. So if you wanted to, it's not so common, but you could also from the Java code call a Pig script, or from your Pig script you could call some Java Hadoop jar to run. Yeah, so that's pretty much Pig. So there's more reading. There's a few other functions that are not so commonly used that are available. You can check out the documentation. Here we've seen the most important ones, I would say. Also worth a mention that we have another competitor to Pig called Apache Hive. So Hive is essentially an even more SQL-like language over Hadoop. Yeah. So it's an SQL style language that compiles into MapReduce jobs in Hadoop. Yeah. So here's a taste of some SQL, which is basically for counting words in this case, just to give a flavor. So we see that it's not really necessarily broken down so much line by line. It's a little bit more declarative than imperative. So Pig is a bit more procedural, while Hive is a little bit more declarative. Yeah, we've got this more moving more towards SQL. My personal preference is for Pig. I like the sort of process of line by line defining what you want to do, especially for running tasks on large amounts of data. But Hive is also popular. Yeah. So they're both kind of similar concepts. Any questions about Pig? Yeah, so the main message then of the class is that we can have higher level scripting languages. This will allow more users to be able to write Hadoop jobs, make it more accessible to use Hadoop. So why not just teach Pig? Why not skip all the Java stuff? Well, if you want efficiency, if you have a massive amount of data, you could probably be more efficient coding the thing in Java. Yeah, you can apply lower level optimizations. So I think Pig is a good idea if you have a sort of a task where you want to maybe run it maybe it's a once-off task. You only want to do it once. You don't care if it takes 6 hours or 8 hours, right? You're like, I'm going to sleep anyways. I just want it to be done in the morning. Do a Pig script and that's all well and good. But if in the context of your company or some organization, if there was some sort of script you're running regularly and you were paying, massive amounts of data, and it took days to run and you were renting machines on the cloud or whatever, then in that case, it would be worth looking at the lower level Java coding to see can you add combiners? What can you optimize on a lower level? That would be more advanced Hadoop programming, let's say, but yeah. So Pig is often very useful, especially if you want to run once off a script and get some results back, and you're probably not going to be running. You don't care too much about efficiency. You just want it to run in some reasonable time. And it's generally a lot easier to program than the Java version. Questions? Thoughts? Okay, so in the lab on Wednesday, we're going to be playing with Pig. There's going to be no Java guide this time. There's no Java. So you're just going to get your enunciado and you're going to have to solve it from the class. Yeah, so we'll have a Pig task, which will be something similar to what we did last week, but a different thing. We're going to look at ratings, if I remember correctly. So yeah. And then we're going to move on to Spark. The next topic will be Apache Spark, which is sort of like a more modern version and a competitor to Hadoop with one specific benefit in particular. Okay, so any questions in Zoom? No? I saw my connection was unstable a little bit during the class. Hopefully it was relatively okay though. Okay, so see you on Wednesday.